The problem is to numerically compute the derivative of the given function and compare it with the exact derivative. We have the function definition f of x equals x e raised to the power x, defined in the interval x to 1.8, from 1.8 to 3, and f prime of x exact value is 1 plus x whole times e raised to the power x. We have 3-point formulas defined in the second cell. Okay, so we have one left point formula, we have the midpoint formula, and we have the endpoint right point formula. We have found from the theory that at the midpoint, the error is 50% of the errors to the endpoints. So therefore, in piecewise implementation to an interval, for the leftmost point, or you can say only at the ends of the interval, we compute from the endpoints, and for all the interior points, we compute by using the midpoint formula. So here we go. I will develop and check the algorithm steps in front of you. So the first step is to import libraries. I have imported the Python libraries NumPy and matplotlib, and they are now part of the program. Now I initialize x, y, and variables. So I first define h equals 0.1. Then I define x domain. So x is equal to, from NumPy, create an array, arange. So arange begins with 1.8. I say start from 1.8. Then I have to provide stopping point. So I say stopping point is 3.0 plus h. This function arange is going to skip the last point. Therefore, I have set 3 plus h. So therefore, the endpoint would be 3 here. And the step size is h. These arguments are fine. Automatically, they will be defined as real. And if you like, you can set the d type, which is behind this bar. Okay, I cannot remove that. So if you like, you can write here code, right? So x is created, and let's see that. That is the facility from Python. So you can instantly check that this array has been created, 1.8, 1.9, and all that, everything has been created, right? That's why we use the interpreters while developing algorithms quickly. So you can test the algorithm on the go. Now I define a variable. I say df exact. df exact. This can easily be computed from the formula. We know NumPy e raised to the power x for x, and times x plus 1. This is the definition of numerical derivative. Oh, sorry, exact derivative. Now for a numerical derivative, this should be from point to point. So for that one, I first define an array. Well, I require the size, and size should be equal to the size of x. So I say n, how many points I have. N points are equal to NumPy size of x, size NumPy size of x, right? So this will give me the number of points which are available in x. So I can check it. I didn't call 10 points. 10 points. So n points are 13. You may count from 1.8, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 points, right? So now I define an array. So another code section. This is available. So I define derivative of f, numerical, and I first store 0 values to this vector. I say NumPy zeros. I require 13 points and of type float. So they will be created. Now the computation of derivative for leftmost point, the index in Python begins from 0. So I say df numerical of 0 at the leftmost point, which comes from the first interval. So I know the formula. I can say the function definition. It was x e raised to the power x. So I can say it is x of 0 times numpy exp of x of 0, right? So this is the derivative at the point. Well, I didn't define function in the program, so let's define that one earlier so that it is exactly like a function definition. So this cell here, I'm going to define the function so that our program is more generic. So I say define f of x. This is the way we define functions in Python. So I say here return with f of x, the value I'm interested, it is x times numpy e raised to the power x, right? So this is the function. Now I can call this function right from my program. Let's make it active for our program. Now the derivative definition would be easier. So first I require the endpoint formula. Okay. The left point, 3 f of x naught plus 4 minus 3 minus 3 4 minus 1 minus 3 4 minus 1 minus 3 f of x minus 3 4 and minus 1 and 4 times f of for function calling, it should be the general parenthesis computed at x naught, function computed at x1 minus 1 times function computed at x2, right? And divided by 2 times h. So this is the definition of derivative at the point first, left point. Now for the interior points, I write in terms of a loop. I write here for I, for k. Okay, for k in range, I have already computed for the first point, which has the index 0. So now index I write from 1 to n points minus 1, right? So I am going to skip the last point. So range is this one. So now it is fine. Now I have to write like a midpoint formula. So derivative f numerical value at kth point, it will be equal to f of x k plus 1 minus f of x k minus 1. So these are the points surrounding the point of interest, and divided by 2 times h. And that's it. So for loop is ended as I get back to the 0 indent position. Now for the last point, so I say df numeric endpoints minus 1 So this will be equal to, I have to consider the right point formula. So x naught, x1, x2, okay, it is at x2, and 1 minus 4, 3. These are the coefficient, 1 minus 4, 3. One minus 4, 3. So the first one. So this will be f of x. It's a bit tricky. So endpoints, minus 1 is this one. So minus 2, minus 3 will be there. Minus 4 times f of endpoints minus 2 x of n minus endpoints minus 2 n plus 3 times plus 3 times f of x endpoints minus 1. So hopefully I have written the correct expression, and parentheses are balanced and divided by 2 asterisk h. Now let's compare the numerical derivative and the exact derivative from plot. I'm not going to use the print statements. So let's plot PLT plot x and the derivative computed exact, and plot it with the red line. And x and df numerical, and plot it with blue color, and I say x label as x and PLT times y label as y. As there are two curves, so there should be legend, and first one is the exact, legend, and the other is the numerical, right? Well, in Jupyter Notebook, PLT show is not necessary. So let's see. It's critical point in the lecture. It seems there is some error. Second last line. Label, y label? No. Y label, but it said there is error in the first expression. Some imbalance of parentheses there. We have to check this expression. So 3 times f of x, okay, 4 times f of x1, and 1 f of x2. Well, this is extra. This was the error indicated by Python, right? Up to this point. Still there is error. And now the error is 1 up to n points, okay? Arange range from 1 to n points minus 1. Yes, this is correct now. So not the colon sign, it is the comma. So I think I am successful. exact and numerical. Both have been plotted, but it has made us in the condition of non-believing. So let's see the numerical values, right? So instead of saying numerical values, let me say error. Error is equal to df exact minus df numerical, right? And this will be computed over the whole, right? Well, and let's see the error values. Error. Behold. So the error values are, say, 0.1, 0.05, 0.06, 0.06, 0.07. So seems to be acceptable, right? Seems to be acceptable. Now, let's change the step size. I have made quite generic program. Let's change the step size. And for the time being, let me change it to a step size of 0.2 so that we can see the difference. I have to run all the cell. Can I run all? Okay, run all. Control plus F9. So from first point to the other. Okay, so the red line is visible. Exact is slightly away, right? Not exact is slightly away. Numerical is slightly away, right? So that's the operation and working of numerical piecewise numerical differentiation implementation.